All right, so start. So thanks everyone for coming despite the weather. So today we are pleased to welcome Aditya Mahajan, who is a professor at the McGill University and who is staying here. He's an invited professor of DATAIA, so he is going to stay here until next June. So feel free to contact him and discuss, yes. And he's going to talk about, as I understood, reinforcement learning with partially observable states.
Yeah, thanks, Eugenie. It's a pleasure to be here. I'm just going to move to that side if more comfortable on that side. So I'm going to be talking about reinforcement learning, and as all of you would know, there has been a lot of hype around reinforcement learning in recent years. It has achieved considerable successes in various domains. Perhaps the most celebrated was AlphaGo being able to beat the best human players a couple of years ago. About a decade ago, there was that RL was able to play arcade games as well as humans. There have been in practical applications a lot of success of RL in robotics and so on. I'd like to highlight 2 points here. First is that the success of reinforcement learning has been based on comprehensive theory. There is a lot of advances that have happened due to deep learning, but at the core, there is a fundamental theory of why learning works in certain environments, and we are leveraging that theory while designing algorithms which work well in practice. And the second is that the theory, for the most part, is restricted almost exclusively to systems with perfect state observation. When we go to more realistic real-world applications, including healthcare, autonomous driving, finance, and others, there is almost never perfect observation. We always have partial observation of the world. So the motivation for this work is, can we develop theory for partially observed systems and have it in such a way that that can inform the design of reinforcement learning algorithms in that setting. So with that view in mind, my talk is going to be organized as follows. I'll start with a background with a review of what are Markov decision processes and what is reinforcement learning, and review what are called partially observed Markov decision processes, or OMDPs, and try to explain why RL for OMDPs is difficult. Then I'll present the main idea that we have in this setting, which is the notion of approximate information states. Before presenting that, I'll review what's called information states in stochastic control and show what do I mean by approximate information state and why that allows us to get bounds while we are doing planning. And finally, I'll say how the idea of approximate information state can be used for analyzing and improving reinforcement learning in partially observed settings. So I'll start with the background review, and just to calibrate, how many of you are familiar with Markov decision processes? Okay, and how many of you are familiar with reinforcement learning? Okay, so I'll be let me at a high level say the motivation for Markov decision processes or partially observed Markov decision processes is decision making in settings where we have decisions to be made in multiple stages and there is some uncertainty. It arises in various engineering applications, but just to sort of set ideas, let's consider the problem of someone going to a casino with a certain amount of money in their pocket and deciding to gamble on a particular, on their favorite game. And each time you place a bet, you have certain probability of winning and certain probability of losing. You may know that probability of winning and losing from past experiences if you are an experienced gambler. And the question is, how should you bet? Maybe you want to stay there for the whole night and you want to see what's the strategy that I can use for betting, which maximizes my profit in the morning when I'm ready to leave. Similar type of problems arise in different things. The simplest way to model this is the notion of Markov decision processes, which I abbreviate as MDPs from now on. The idea is that there is certain environment which has a state. There is an agent which is interacting with an environment. The environment is a Markov process. That means the environment evolves in a Markovian manner, given the past state of the environment and the actions taken by the agent that determines what will be the next state of the environment. The agent gets this observation, and every time the agent acts, the nature yields a reward, which is a function of state and actions. The agent is interested in looking at all the history information that it has, which could be all its past observation and action, and use that entire knowledge to take an action at time t. The decision rule which is used to take an action is called a policy, and the objective is to choose a policy over time in order to maximize the expected discounted reward. The objectives could be different also, but I'll stick to expected discounted reward just for the sake of consistency. Now, at the face of it, this is a challenging problem, and the reason for this is the fact that I'm allowing my agent to use the entire history of observation. If I want to do this in a brute force way, I'll think of all functions which map this history to actions. The size of the history is increasing over time, therefore the cardinality of the function space is increasing double exponentially in time, and if I just do a brute force search, that's going to be considerably higher. So the key question is, how can I search for a policy efficiently? There are two fundamental results in the literature regarding this. It's not typically presented like this in the literature, but I'd like to think of it this way. The first result is due to Blackwell, which is the principle of irrelevant information. And basically, one can show that since I have access to the state of the system, I do not need to keep track of the past realization of states and actions. So there is no loss of optimality in choosing the action just as a function of the current state. This reduces the search complexity from double exponential in time to just exponential in time. Not good, but somewhat better. And the second is the celebrated principle of optimality of Bellman, which says that rather than solving this as a functional optimization problem where I'm optimizing over functions over time, I can actually think of this as a fixed point problem where I'm optimizing over certain choices of actions over at each state. So from a functional optimization problem, we can reduce it to a parameter optimization problem and finding the fixed point of an operator. And this has a complexity which does not depend on time. So these two allow us to solve, at least conceptually solve, all Markov decision processes. There's a lot of computational issues which I'm not sort of going to completely ignore in this talk. Now, what about learning? So in the standard setting, the learning idea is that the agent is acting in an environment where the reward function and dynamics are unknown, but the agent can interact with the environment. It takes action, it receives observations, and this cycle continues. And we want to design an algorithm which asymptotically in time, identifies an optimal policy. There are two broad classes of algorithms which do that. One are value-based methods. These approximate the Q function or the Hamiltonian of the function of the system using temporal difference. This is Q learning by Watkins, and there's a lot of subsequent work on that. The other is policy-based methods, which say we'll look at a class of parameterized policies, compute the performance gradient, and try to optimize that using gradient descent-like methods. And there's a significant amount of work in this. Now, this is all well understood and works really well in practice. So the key question is, why is learning difficult in partially observed environments? To understand that, let's go back to planning. When I know the system model, what is the solution for partially observed environments, and why does that solution fail when we go to learning? So partially observed environments, as the name suggests, is the setting. It's the same setting as before, but my observations are not the state of the environment, but the agent observes a different observation. So there is some observation at each time, which depends on the state. This could be a stochastic function of the state. The rest of the setting is the same. But because the observations are now not the state, when I'm choosing the policy is a function of the past observation and actions, rather than the past states and actions. So the same conceptual challenges as before. Action is a function of the entire history. The problem is double exponentially complicated in time. And the basic solution idea is the notion of a belief state, sometimes called sufficient statistics, or sort of the nonlinear filter for this problem. And the idea is, if I don't know the state, I'm going to form a belief on the state. So what is the posterior distribution on the state? given all the past observation and actions. One can show that the next belief state is a function of the current belief, observation and action. This is simply the nonlinear filtering update equation for this nonlinear filter, and that this belief is sufficient to evaluate rewards. That is, if I look at the expected value of the reward at current time, conditioned on all the observation and actions, that would just be a function of the belief and action. So in statistical terminology, a belief is a sufficient statistic for all the past data in order to evaluate action. So using these two properties, one can show that the belief process is a perfectly observed controlled Markov process. I'm in a higher dimensional space now because I'm no longer in a state value process. This is a belief on state or probability distributions on state, but modulo technical complications, conceptually everything is the same, and we can reuse existing ideas. And essentially we get that the structure of optimal policy is we can choose actions just as a function of the belief, and that we can write down a dynamic program where belief is the state. So this allows us to use the machinery of MDPs for partially observed systems. There's some issues with computational methods because we now have distribution valued state, but there's a huge literature on that. I'm not going to try to provide an overview of that, but we know really well how to solve planning problems with partial observation. But what about learning? So recall the basic idea for learning was that I have access to state and I'm going to either learn the Q function or try to learn the gradient of the policy based on the state. In partially observed settings, the state was the belief of the true state of the system given the observation, which depends on the system model. So if I do not know the system model, I cannot construct the state. And if I cannot construct the state, then all the existing RL algorithms do not work. Okay? Now, given this, there are two approaches which have been taken in. On the theoretical side, people have come up with various alternate notions of state. These include predictive state representations, bifurcation metrics, and so on. These have very good theoretical guarantees, but they're difficult to scale. You cannot leverage the deep learning solutions to solve these problems. And on the practical side, people have simply said, well, let's forget all the theory. I'm just going to take previous K observations and call that a state. It does not satisfy the properties of a state. Doesn't matter. I had a deep learning algorithm where at some stage I was using a convolutional neural network. I replace that with a recurrent neural network, do hyperparameter tuning, and it works. And there is considerable empirical literature that this works well. But there is no theory. So our motivation is, can we develop some theory which will help us to understand why the practical algorithms are working? Okay? And I'm going to present sort of result of two papers. And this is a theoretically grounded method which provides which helps us understand what's happening for RL in partially observed environments and has strong empirical performance. So the first result is regarding approximate planning. And in order to understand that, I'm going to sort of change the model slightly. So since we don't have a state space model, I'm going to actually just work with an input-output. I'm going to assume there is some stochastic system. The system has two inputs, a controlled input which the agent decides, a stochastic input which is determined by nature, and it gives two outputs, the observation yt and the reward rt. These in general could be some function of the entire sequence of inputs to the system. Okay? My timing order is agent chooses what the action is, nature chooses what the disturbance is, agent observes the output and the reward, and chooses the next action, nature chooses the next reward, and so on. The setting is same as before, just for ease of notation, I'll call HT as the history of all observation and actions to the agent. The agent chooses an action as a function of the history, wants to choose a policy to maximize the expected discount return. Okay? Now, I'm going to present the idea of an information state. It's a well-known notion in stochastic control, but somehow it's not so well-known in the AI community. Informally, one can think of an information state as a compression of all information, which is sufficient for performance evaluation and predicting itself. And as I said, this is an old concept. There's a bunch of papers in the 60s and 70s which were talking about that. It's also related to other ideas which are used in the AI community, including biosimulation, predictive state representation, epsilon machines. I'll not point out that correction during the talk, but if someone is interested, I'm happy to talk it offline. The main idea is as follows. Let's revisit the notion of sufficient statistics. So sufficient statistics says the following. Suppose I have some state, an observation, some actions. This is just one step problem. And I have a reward, which is a function of state and action. And I'm interested in choosing an action to maximize the expected reward. Let's consider a compression of the data, Z to be some function of Y. This statistic is called sufficient for evaluating the reward if the expected value of the reward given all the data and action is same as the expected value of the reward given the statistic and the action, which is another way of saying that the expected value of the reward given data and action could be written as some function of my sufficient statistic and action. Okay. Now, in dynamic programming, a sufficient statistic is not sufficient for dynamic programming. In particular, if I have a sequence of sufficient statistics, I cannot do dynamic programming. To do dynamic programming, I also need a self-predictive property. That is, the sufficient statistic at time t plus 1, conditioned on the entire history and action, should be same as the sufficient statistic at time t plus 1, conditioned on the sufficient statistic at time t and action. So if I have these two properties, I can do dynamic programming. Formally, given a state space Z, I would say an information state generator is a tuple consisting of the following components. It's a sequence of history compression functions which map the histories to state. A reward predictor which takes the information state and action and gives me a reward. And a transition kernel which takes the information and action and gives me a distribution. If this tuple satisfies the following property, one, that it is sufficient for a performance evaluation, and second, it is sufficient for predicting itself, then it is called an information state. Okay? So an information state is a self-predictive sufficient statistic. And it's rather straightforward to show that if I have an information state, it always leads to dynamic programming. And essentially, I can write down a dynamic program where my value function is looking at the reward as a function of the state and A. This is the reward predictor that was part of my information state, and the expected value of the next value function given the transition kernel, which is part of my information state. And if I solve this fixed-point equation and compute the corresponding policy, that policy is optimal in the original mode. Okay. Again, this is all classical result. I'm just presenting it just to fix notation, essentially. Now, a lot of the standard results in the literature can be thought of as special cases of an information state. In an MDP, the current state is an information state. In a OMDP, the base state is an information state. If I look at other models, for example, MDPs with delayed observations, then I can show that the delayed state and the actions taken since the delayed state was observed is an information state. If I have OMDPs with delayed observation, I can come up with a similar notion of state. If I have a linear quadratic Gaussian models, one can show that simply the conditional estimate is the information state. I don't need other parts of the distribution. For other specific models, we can come up with other notions of information. I would argue anytime you can do a dynamic programming decomposition, that is by identifying an information state. Now, we can use this basic idea to come up with a notion of approximation in dynamic programming. So the main idea is as follows. I've defined a notion of information state in terms of two properties, which I called P1 and P2, which was something is equal to another thing. What happens if these properties are not satisfied exactly, but approximately? If they're satisfied approximately, I'll call it an approximate information state. Okay? And what we'll show is that if I have an approximate information state, I can always do dynamic programming. And from that dynamic programming solution, I can argue that that is approximately optimal in an appropriate sense. And this allows us to recover and sometimes improve many of the existing. So formally, I'm going to define an epsilon delta approximate information state as a generator which consists of same components as before, a history compression, a reward predictor, and a dynamic predictor, which satisfies the properties P1 and P2 approximately. That means that if I look at the expected reward given history and actions, that should be within an epsilon ball of the reward that would be prescribed by the reward predictor, given the approximate information state in action. And if I look at the distribution of the next state given history and action, that should be within a delta ball of the distribution on the next information state given the current information and state in action according to my information state predictor. One technicality here is I'm talking about distances on probability measures. So I need to be precise in terms of how I define that. For now, I'll just say that this could be any integral probability metric on probability spaces, but the nature of our approximation will depend on the choice of metric that we put on probability. Okay. So the key result is I'll write down the same dynamic program as before. I'll pretend this made up dynamics and rewards are exact, and I'll solve a dynamic program based on this. This gives me a policy, and I'm interested, a value function and a policy, and I'm interested in two questions. One, how far is this value function from the optimal value function that I could have obtained had I keep a track of the entire history of the system? And we're able to bound that this is related to some bound alpha, which depends on epsilon and delta, which were my approximation balls for the dynamics and the reward. And it depends on a property of the value function, which depends on the choice of metric on probability spaces. I'll go into a bit more onto what this thing is a bit later. So this depends on the metric. The other is, and this is the more interesting problem, I really don't care from a practical point of view how good my value function approximation is. What I care is if I use this dynamic program to find a policy, and I use that policy in the original model. So I find a policy pi hat star, and I use a policy which is pi hat star composed with my history compression function. How well does this policy do in the real environment? And we are able to say that this difference in performance is also twice alpha, where alpha is the same quantity as before. Okay. So once I have an approximate information state, I can write down a dynamic program, and this very easily gives me what are approximation bounds on using that policy in the true model. Now, just certain comments. There are two ways to interpret the results. One is to say, given the information state space, find the best compression that I can get. But the second is that given a sequence of compression function, find the approximation error. So a lot of time, at least in the control literature, people have been focused on the first question, which is to say, what's the best representation that you can find? I would argue that it's more interesting to think in terms of the second representation, because if you look at what is happening in the empirical side of things, someone is using a given recurrent neural network, and I want to say how well that does. So I'm not really in the question of how do I improve my representation. I'll simply try to evaluate what's the error given a particular representation. Just said that, and the result depends on the choice of metric. Our results have to use on what are known as integral probability metrics, but these include many of the commonly used metrics, including total variation, others. So it is under some restriction, but it's not too restrictive an assumption on the type of metric that I have to use on my probability space. Now, let's look at some examples. So the simplest model is the following. Suppose I have some real world environment with some dynamics P, reward R, and I build a simulation model for this. I'll call the simulation model P hat and R hat, and I do my design based on the simulation model, either using RL or using planning or whatever, and I'm interested in what is the model mismatch error. If I use the policy corresponding to this model in my real model, how much do I use? Okay. So I can really cast this as a question of an AIS. My AIS is really, this is an MDP, so my history compression is just identity. I just look at the current state. My P hat, R hat, or whatever are the P hat, R hat for my approximate model. Based on this, I can compute what is the epsilon, which is the truth norm error between R and R hat, and I can take delta, which is the distance between these two transition kernels, supremized over all state and action. And based on this epsilon and delta, if I choose my distance as total variation, I get a certain bound. I'll not really pass the bound too much, but simply say this recovers sort of classical bounds on total variation error, which are due to Muller. If I use Washoe time distance, then I recover the bounds which were due to Sadi, Misra, and Littman recently. So very easily we can recover classical results in the literature by just doing things in terms of an AIS. Next is the notion of feature abstraction. So oftentimes if I'm working in a large state space, we would come up with certain feature maps which map this state space into some smaller state space. And depending on the choice of this feature abstraction, I would have certain dynamics and rewards in this lower dimensional space as well. And we have the same question as before. If I choose a plan according to a policy according to this feature space S hat and use that policy in the true model, how much do I lose in performance? And again, I can think of this feature map, whatever is the dynamics and rewards that come up as this feature map, as an epsilon delta AIS, where I can quantify what epsilon and delta are as a function of this feature map. And if I choose my metric as total variation, then we get certain bounds which actually improve the existing results in the literature by Abel and al. By a factor of 1/1 minus gamma. Gamma here is our discount factor. And if I use the distance as Washoe time distance, we recover the bounds which were recently using Gileda and all for Washoe time distance. So again, once we have the framework for AIS, we are very easily able to recover existing bounds in the literature by just doing them as special cases of AIS. Any questions so far? The span of the reward function, so the supremum minus the infimum. Okay, so now to getting some bounds for OMDPs. So again, so one way to solve OMDPs is you have a belief state which will be some simplex in Rn. I can quantize that belief using some sort of discretization. I can try to find a policy for this discretized model, try to transfer it back to the original model, and ask how much do I lose due to this quantization. And again, one can think of the quantization as something of radius epsilon, and this would be an AIF where I can quantify what, given the quantization radius of these cells, what is epsilon and delta that we were talking about in the AIS approximation. And based on this, while using total variation as a distance, we can get what would be the approximation error. And this is similar to the approximation bounds which were recently presented by François Levé and all. We actually improved the bounds of François Levé by a factor of 1/1 minus gamma. This in itself, the improvement is not surprising because these results were using the previous results that I had mentioned for total variation. So since we improved that bound, that's the same improvement which is carrying over here. But the important thing is that we can again recover classical approximation bounds in the literature with sort of very simple corollaries of the approximation bound for AIS. So I'd like to conclude this section by saying that I believe that AIS unifies many of the approximation results in the literature, both for MDPs and POMDPs, and I think it's a really nice, conceptually clean way of thinking about approximation in both perfectly observed and partially observed. Any questions? So let me go now to the last part of the talk, which is for reinforcement learning. So let's see what people are doing in practice in reinforcement learning. So suppose I had some partially observed environment. What is normally done is you feed this into a recurrent neural network. You take the state of the recurrent neural network and use that as an input to your favorite Q-learning algorithm, and do end-to-end learning using gradient descent, and in most cases, distinguish. Now, what's happening behind the scenes is that the recurrent neural network acts as some form of a recursive state generator. So the state of the recurrent neural network is some function of the previous state of the recurrent network, the observations that we get from the environment, and the actions taken by the agent. And in the simplest setting, the Q-learning algorithm which is being run is the standard Q-learning algorithm where people simply treat the state of the recurrent neural network as a state of an MDP. So this is not easy to analyze, and I'm going to spend some time trying to highlight why is this Q-learning algorithm not easy to analyze. So before doing that, let me go back to what's happening for Q-learning in MDPs. What's the standard convergence argument for Q-learning in MDPs? And that allows us to see why Q-learning for POM-DPs is difficult to analyze. So in an MDP, what we have is a dynamic program. So my value function is some supremization over a Q function, and Q function is given like this. What we do in Q-learning is say, suppose I don't have access to this dynamics E, but I can take a sample from this. So I would run an environment. I'll recursively keep track of a Q function. The new Q function is the old Q function plus some learning rate type, a sample of the reward that I get, plus the value function at the next state that I observe, minus whatever my current Q function was. This is known as temporal difference learning. And the key intuition is that what I'm getting here in Q-learning is an unbiased sample of the expectation that I wanted to compute in dynamic programming. And therefore, I can say from standard arguments from a stochastic approximation that if I'm getting an unbiased sample from expected value, then this is a stochastic approximation of dynamic programming. And therefore, this stochastic approximation will track an appropriate ODE. And since I'm doing dynamic programming, there is an operator here which was updating the Q function. I'm looking in the discounted setting, so that operator is a contraction. So I'm in a setting where the ODE, the corresponding ODE has a unique, globally asymptotically stable equilibrium point. Therefore, whatever is happening in the discrete iterations would converge to the solution to the unique, globally asymptotically stable equilibrium point of the corresponding ODE. Okay. So this is all standard analysis for how Q-learning works. What's important to realize is that the only sort of thing that we are doing is I have a dynamic program which has a unique fixed point. There is some expectation in there. I replace that expectation by an unbiased sample, and then from standard stochastic approximation theory, we can say that those iterates will converge. Now, what happens when I look at the same iteration for OMDPs and try to do the analysis? The real issue is that there is no unbiased sample from a DP step here. I cannot just take this guy and try to write down a DP corresponding to this. Suppose I blindly write such a DP. I say there's some Q function which is expected of the current reward given the current state and action, and some dynamics on the current state and action. Remember, this ZT was the state of an RNN. This reward as a function of the state of the RNN is not going to be time homogeneous. And the dynamics of the RNN, there's a typo here, this should have been a Z, not an S. The dynamics of the RNN are not Markovian. The reason they are not Markovian is because they depend on the observations from the environment, and we do not have access to the state of the environment. Therefore, the dynamics, just as a feature of the agent state, are not Markovian. So, I don't have a standard dynamic program. I have time-varying rewards, non-Markovian dynamics. I cannot simply say there's going to be a fixed point for this, and this thing is going to track the fixed point. Okay? So we need to do something slightly different as far as the theory goes. But there are other things which behaviorally RL for POM-DPs works differently. So one interesting thing is that exploration policy matters. So here I've taken some simple model where blue and red are two different exploration policies. What we get is that Q-learning ends up converging. At a high level, the reason Q-learning converges is because we are doing we are reducing the step sizes, but the hard thing is to show that it would converge almost surely. Along each sample path, I'll converge because I'm just using temporal difference learning or stochastic approximation, but whether for all sample paths I'll converge to the same point is difficult. But in practice, it does converge to the same point. This is one model where we use a particular exploration policy, here's a different exploration policy, and simply by changing the exploration policy, where I converge to is different. So the results that we should get should capture this behavior, that what I'm converging to depends on the exploration policy that I'm using. So for this, let us to think in terms of what's really happening, and I believe that we can completely quantify what's happening to the convergence under the following assumptions. So I'm going to restrict myself to the tab. Yeah.
Learning is on policy.
I am analyzing the simplest setting. So I'm looking at off-policy Q learning. This is the simplest setting of this. There's a behavioral policy according to which I'm acting, and I'm simply updating my Q function. And I hope that this thing converges to something, and I'll take the epsilon greedy policy. I'll take the greedy policy with respect to my converged Q function that I do. And this is just the simplest setting to analyze. If we cannot analyze this, then more complicated settings are harder to analyze.
Here, Z is a function of previous observations.
Yes. So this is the thing, right? So Z would be whatever is my state of my RNA. So it would be a function of the previous observation and actions as the rectal neural network compresses it. It's just, if not, you can just think of this as some updatable function, and I'm keeping track of some values of the past observation and action. Okay. Simplest setting would be Z is equal to just the current observation. So you mean here?
Yes.
Yes. So this is that the reward changes over time. Okay? So let's think my reward depended on the state of the environment, but I'm only keeping the current observation as my state. So if I find the expected value of the reward conditioned on the current observation, this will keep on changing as my observation changes. It's not a fixed function because I don't have, if I was keeping track of the entire history, I'll have a consistent, time-consistent belief. But because I don't keep track of an entire history, I have time-varying beliefs. So my expected reward given this is not time homogeneous. It's, if I think of it as a function of Z and A, that function is time dependent. Other questions? So we're going to analyze Q learning in the following assumption. I'm restricting to the tabular setting. That means state, action, and the agent state are finite valued. This can be relaxed, but just to sort of analyze the really simplest setting, I'm making this assumption. The second is that there is an exploration policy, that the agent acts in the environment according to a policy which maps the agent state to distribution over actions. And I'm going to assume that under the exploration policy, the Markov chain, which is the state of the environment, observation, agent state, and action, has a unique stationary distribution, which I'll call Xi. Furthermore, this Xi is bounded away from 0. This can be thought of saying that all environment state, observation, agent state, action pairs are visited infinitely often. If I don't have multiple classes in my Markov chain, it's all a single recurrent class, and all states belong to the same recurrent class. Okay. I'm going to assume that the learning rate that I use is count-based learning rate, number of times I visit the particular agent state action pair divided by total number of, whether I visit the state action pair divided by total number of time I visited that agent state and action pair in the past. This looks like a standard assumption, but this is sort of our strongest technical assumption because we cannot use standard stochastic approximation, and the analysis relies on certain ideas from Markov chain, which I can only use when this assumption is satisfied. So it's relatively easy to relax the first assumption. Second is standard in all convergence analysis for reinforcement learning. Third, in our case, although it doesn't look like it, is the real restrictive assumption. Okay. Under these assumptions, I have some stationary distribution Xi. I'll define a reward function and a transition kernel based on Xi. I'm using the notation Xi S given ZA means just I have a joint distribution on all variables. This is just the corresponding marginal distribution according to the joint on all variables. So xi is assuming that my stationary distribution has something on the state. What's the belief on the state according to the stationary distribution of the Markov chain, and averaging the reward according to that. And the dynamics are similar. It looks more complicated, but I'll say what's the belief on the current state according to the stationary distribution given the current agent state and action. How does the environment state evolve? What is the observation as a function of the next environment state, and whether the next agent state is equal to the update that I was using. So I define a reward function and a transition function. This gives me a dynamic program, and let v xi and q xi be the solution of that corresponding dynamic program. Then what we can show that under the assumptions that I mentioned in the previous page, the iterations q hat t of the q learning for OMDPs converges almost surely to the solution of this dynamic program. And this result has that feature that what I converge to depends on the stationary, depends on this xi, which is the stationary distribution induced by my exploration policy. So it's not surprising that when I use different exploration policies, I converge to different limits. Okay. So convergence is good, but convergence is not sufficient. And the reason is the following. So I can converge, but I can converge to really bad things. So here I'm showing the example of what happens when I use two different feature representations. So in one case, the green line, my agent state is nothing. Agent state is always constant. Okay? So my agent does not see anything from the environment, just keeps connecting, it gets the rewards, and it updates the Q function according to the reward, and that converges to some value. In the second case, the agent is keeping track of just the current observation. And it's not surprising that when you keep track of the current observation, what you converge to is better than when you don't keep track of any information. So although I'm converging in both cases, what I'm converging to is different. So we have to quantify the quality of the converged solution and not just the fact that we are converging. What's more interesting here is that this is just saying that the Q iterates are converging. In practice, what you would do is, I am interested in a policy that I can use in my model. So when my Q iterates converge, I'll go to this dynamic program and I'll find a policy from this step. This is called the greedy policy with respect to my Q function. I'll use that greedy policy in my environment, and I want to see how well does that greedy policy do. And in this example, there's a stark difference in the performance of the greedy policy, that the greedy policy actually converges relatively quickly when I'm using one observation. When I'm just using no observation, the greedy policy keeps on oscillating a bit, but it's significantly worse than what I'm doing. And what I'd like to quantify is how far is the performance of the greedy policy that I got from the optimal that I could have done had I kept track of the entire information. So that would allow me to say whether I have a good solution or not. Now, how do we quantify the quality of the converged solution? And there's the simple observation that what I'm converging to, this R psi P psi, I can just view this as an approximate information state. As some true dynamics, I'm saying I'll choose a policy according to these dynamics. How well does this policy do in the original model? So I can quantify epsilon and delta corresponding to these. This is just same epsilon and delta as before, except now just to have a clean looking result, I'll maximize this over what happens over all time. And if I take the policy that converges with my history compression function that was being used, the performance of this policy as compared to the optimal performance, this is the same bound that I had before. So once we have that Q learning is converging to the solution of a dynamic program, we can use the approximate information state results to very easily bound what is the performance loss that happens when we are doing this. Okay. This is good, but can I take now these results to go back to reinforcement learning and try to say that there's some way to improve existing algorithms? So the main idea is as follows. What we are converging to depends in terms of the AIS loss, which depends on these two terms, epsilon and delta. If I minimize epsilon and delta, I will minimize the approximation loss. If I want good learning, that should be something which minimizes the epsilon and delta of my representation. So I can just use, let's say, a squared combination of epsilon. Perhaps I'll have something which does better. So we call this Q learning with AIS losses, or recurrent Q learning with AIS losses, or RQL-AIS for short. And the main idea is, in this case, I'm presenting this as a modification of a state-of-the-art algorithm, which is known as R2D2. And R2D2 is this block. It has a Q function, it has a target Q function, it does some comparison with it, then it has an epsilon greedy block, which chooses a policy, and this thing goes back. What I'm going to do is I'll add a block which I'm calling the AIS block. This AIS block consists of a recurrent neural network, let's say an LSTM, and an AIS predictor. This LSTM compresses all the past observations and actions into a state, and the AIS predictor takes the state and tries to predict a reward function and a distribution over the next observations. I'll compute this epsilon and delta from samples here and take epsilon squared, delta squared as a loss that happens here and minimize, optimize the parameters of this LSTM and this neural network using gradient descent. And I'll keep on using whatever the Q-learning algorithm was doing in the Q-learning. Okay. And let's see how this does in practice. So I'm going to evaluate this on this class of benchmarks known as mini-grid. These are different environments where agent has to find a way from a source to a goal state. Agent has some area that it can see, and you can perhaps see that with this light gray colored block here. The dark black is what the agent cannot see. So whenever there are walls, agent cannot see beyond the walls. It can only see a certain rectangle around its position. The environment can be more complicated. There can be doors, keys. Agent cannot look beyond doors. For certain doors, it needs a key to open the door and can only go through that and so on. Okay. And in this, I'm going to compare two algorithms. The baseline is R2D2, which is a very competitive algorithm for form DPs, which had been proposed by DeepMind. And the second is we're going to take R2D2 and add AIS losses to it. For full disclosure, we are actually not implementing R2D2. This was too optimized for our taste, that this was implemented in terms to run at multiple clusters. We only had access to one cluster, so we have simplified the R2D2 algorithm to just run on one cluster rather than multiple clusters. So if one compares with true R2D2, things might be different, but we don't have hardware to do that. So how does this work? So what I'm doing is on the left, I'm showing the learned policy and how this agent is behaving, and it's very clear from these plots that the agent learns how to go. These are training curves, and all these environments are parameterized by something. I'll not completely parse it, but here F9 basically means this is like a 9 cross 9 grid. N2 means the number of blocks that there would be, number of openings that there would be, or something like that. And the larger the number, the more complicated the environment. And we see that for small environments, both of these are learning relatively quickly. I'll not read too much into the fact that we have slightly less variance than R2D2, or that we are learning slightly faster than that. To me, this is that both are learning approximately the same. When we go to larger environments, we are learning slightly better than R2D2. The same thing happens in other environments. So this is like the previous one, except these things are lava. If you touch them, then you die. You still have to find a path to go from the source to the destination, which we are doing. And if we go to more complicated environments, things are more interesting. This is really a difficult environment where the agent has to figure out that there is a key in the environment. It has to open certain doors to reach that key, take that key to go to the goal state, drop the key, and then reach the goal state. Okay? All of this is being learned just by end-to-end learning. When we are in small environments, both RQL-AIS and R2D2 learn well. When we go to larger environments, R2D2 fails to learn, while when augmented with AIS, it is still learning. The fact that R2D2 fails to learn is not surprising. One of the reasons for these mini-grid environments was that these were designed as something for curriculum learning. So you're supposed to learn the simpler environments and then train the agent on harder environments, while we are just doing end-to-end training directly on the harder environment. What's surprising is that with this small modification, we are able to learn this. And this feature is across multiple environments. Our paper has about 24 environments. I'm just listing a subset of these here. And I can roughly say that when I'm in simple environments, both RQL and R2D2, RQL AIS and R2D2 learn reasonably well. But when I start going to complicated environments, RQL AIS continues to learn while R2D2 stops learning. Okay? So we have that by taking this basic insight that we had from theory and adding it to the implementation, we get something which improves existing algorithms. So with this, I'll stop with the concluding message that I believe that AIS is a very clean conceptual framework for approximate planning as well as learning in partially observed systems. We have papers which have used these ideas to show that they generalize in other settings as well, including sort of compression of the observation, action quantization, lifelong learning, multi-agent teams, and Markov games. We have ongoing work where we are looking at similar results in other settings, including model-based RL, offline RL, and inverse RL. And I personally feel that this provides a good building block for multi-agent RL, which is sort of the main focus of my research. And if you have any questions or remarks on that, I'll be happy to discuss. Thank you for the attention. And I just mentioned I should acknowledge funding agency by NSERC and DATAIA. Thanks.
Start. So at the very beginning, you said there can be like two goals about epsilon delta. One is to really find the best with the best epsilon delta, and another given something, however.
Yeah.
But I'm because I kind of more familiar with different type of RL. So I wonder, but given, is it easy to compute this epsilon delta if you don't want to learn it as you do? But
no. So that's a good question. And learning epsilon is relatively easy. Epsilon is just the soup norm between certain things. And if I replace if I replace that with something smooth, I can learn it relatively easily. Delta is more complicated. So in the simplest setting, suppose I take delta to be the Wasser's time distance between two distributions. In principle, I can compute Wasser's time distance. I need to solve a linear program to do that. I cannot be solving a linear program at each iteration. That's just too complicated. So what we do in practice is, and I briefly mentioned that in this slide on learning, one of the choices of IPMs that works really well is what's known as MMD, maximum mean discrepancy. If I get this. So one of the choices is this maximum mean discrepancy. Maximum mean discrepancy computes this thing based on the norm on a reproducing kernel Hilbert space. And the key idea is, in order to do my learning, I actually do not want to compute the distance. I want to compute the gradient of the square of the distance. So I said delta squared. And that's sort of done specifically because gradient of delta squared can be computed efficiently. If I was interested in computing this delta itself, that would be complicated. But gradient of delta squared, I don't remember the exact algebra on the top of my head, but we have that in the paper. And that has an expression which is easy to do in a batch-based, sample-based manner. So in practice, we can compute the gradient easily. Computing the actual error requires solving, again, an optimization problem. MMD can still be computed a bit more efficiently than Wasser's time distance, but there is a loss in computing that at each iteration. There's a computational price at computing it at each iteration, so we don't want to do that.
Use something like Gaussian kernel.
Yes, we have tried with both Gaussian kernels and Laplace kernels, and for the specific choice of the problem, the choice of kernel makes a bit of a difference.
And the issue with Wasserstein is that you have a supreme or Lipschitz function.
Yes, so when we use Wasserstein distance in practice, what we do is we bound the Wasserstein distance by total variation using the Pinsker inequality and compute the derivative of the square of total variation. So that essentially becomes KL because, bound the Wasserstein by KL and use that to approximate things. But using Wasserstein at each iteration in an RL would be computationally too expensive to do. Yeah.
Yeah, there's something that I must have missed. I didn't understand how you learn this approximate information state.
Okay, so what I'm doing is, so what I have in here is R hat and P hat. So I say I have an RNN which will generate some Z. And let's say my reward, I take some simple a neural network with certain outputs as my reward if I'm in the finite state. So this is just a neural network with n-dimensional output. And for my observation prediction, I'll assume it is in some parameterized family. So let's say this was a mixture of Gaussians. So what I'm predicting from here is I fix the number of mixtures as a hyperparameter, and I'm predicting the means and the variances of that mixture through a neural network. Given this estimated reward function and this, I'm computing now the gradient of epsilon squared and delta squared and doing back propagation to learn the parameters of the LSTM and the parameters of these representations.
This is done concurrently to the reinforcement learning?
Yes, this is done concurrently to Q-learning. In theory, I should be doing this at a faster or slower timescale, but in practice, you just use the current recommendation for deep learning, which says use a learning rate optimizer like Adam here rather than choosing learning rates according to theory. And we do the same thing here, and that seems to work.
Is it true that the theory that you presented does not take this part into account?
Yes, so the theory does not say that jointly this will converge. Right? So, in principle, we can show this will converge. Like multi-timescale analysis works, but there's a conceptual thing there which I don't know how to solve, and that is if I'm doing optimization of my representation, the overall end-to-end cost as a function of this optimization, these parameters of this is not convex. So in multi-timescale, I'll have a situation where one of the timescales is not convex. So I am not aware of any theoretical result for multi-timescales which does a complete characterization of convergence when you have when both the ODEs are not globally asymptotically stable. And if I have non-convexity, best I can hope for is local asymptotic stability. So if I simply impose an assumption that this thing is globally asymptotically stable, then the theory works. But that's not there in practice, so we don't know what to do there. So we can say something in theory, but it would not match to what's actually being done in the implementation. Sure.
So here you focused on partially observed. But I guess you can apply the same thing for large state space.
Yes.
Right?
Yeah. And
you observe the state that you want to.
Yes. And that has been done in the literature. So, like one of the papers that I mentioned here. So this Gelada et al. They have this paper which is called Deep MDPs. And that's precisely the idea. What they're doing is that this guy now is a neural network for them. And they are not taking these losses and using that back, but they are using basic ideas that you can use this for MDPs and do this. Actually, we did some experiments which were interesting. I don't have the plots for these here. So what we said was, if I look at any RL algorithms for MDPs, that is doing some sort of, like this setting, that's doing some feature abstraction. So that makes it a POMDP, which means that if I use a POMDP algorithm for an MDP, I should do better. And numerically, we find that that is the case, that if you use the entire history, you will do better than not using the entire history. But it's too much computationally, it's too expensive to do that for MDPs, and sort of people have really figured out how to do the basic thing well, so there's no real reason to do that, but you still get improvement over just current state-based results if I start using the entire history in MDPs as well.
Just to know, states are
You mean for planning or for learning?
in general.
So, I mean, so the message that I'm saying is that in learning, one cannot construct belief states because I don't have access to a model. In planning, the way you construct belief states is I have this nonlinear filter that I have to do. So you take your favorite tool from nonlinear filtering and use that. So people have used some sort of kernel-based methods. Particle filters are very popular. So sure, if you believe that this is sufficiently regular that you only need the first few moments, one can do that as well. Like there's a lot of work in control where people use variations of Kalman filtering to do that, even though the system does not satisfy the properties of that. So you use extended Kalman filtering and its variations, and that works well in certain applications. There are a lot of like these point-based methods essentially keep track of belief in terms of particles, and each particle corresponds to a point in the distribution of the belief, and you have the fancy ways of adding particles or removing particles to make sure you have enough diversity. So there is a huge literature which has tried essentially all methods for nonlinear filtering can be adapted to keeping track of belief for POMDPs.